So far in this section on trigonometric functions, we looked at differential calculus, and we discovered that the derivative of sine x was cos x, and the derivative of cos x was negative sine x. So what we're going to do in this section is to develop these in order to find the integral for sine and cosine. So for instance, if we imagine that we had a function cos x, so if we imagine that we just started with a function cos x, and we wanted to find the integral of cos x, we would need to think what our function would be such that once we had differentiated it, it would end up as cos x. And we should be able to make connections here to realize that if we wanted to end up with cos x after we differentiated it, we must have started off with sine x. However, because it's going to be an indefinite integral, there will also be a plus c, some additional value which will disappear when we differentiate it, but it could have taken any value. So there'll be some constant c as well, but the integral of cos x would be sine x plus some constant value c, and similarly here we could work backwards from here to ascertain that the integral of sine of x would be negative cos x plus some constant c, and if we wanted to, we could find the derivative of these to confirm that that's what we arrive at. When we are looking at the composition of sine or cosine with a linear function, again, if we were starting off with, for instance, here, cos ax plus b, and we wanted to integrate that with respect to x, what would our function be such that once we had differentiated it, we would end up with cos ax plus b? So we've established here that the integral of cos would be sine, so we can recognize that it would be sine ax plus b. But if we're just starting off with this section here, remember that when we use the chain rule to differentiate it, we would differentiate sine to get cos, so we'd have cos ax plus b, but we would then multiply it by the derivative of the function here. So we multiply by a. So if we just differentiated this function here, we would end up with a cos ax plus b. But that's not what we want, so we would need to divide through by a in order that we just end up with cos ax plus b. So our final integral would be 1 over a sine ax plus b plus some constant value c. So here are 3 questions. I'll invite you to have a go at these yourself, or possibly follow the first one through first and then try the remaining 3. In the first instance then here we can just recognize that we've got a constant here, 3, so we could take the 3 out and then say 3 times the integral of sine x. We've just established that the integral of sine x is negative cos x plus c, so the solution here is going to be 3 multiplied by negative cos x plus c, and we could just simplify it like that. For part B, we are going to use the composite, so it's going to be, we're going to use this rule here that we looked at previously, so it's going to be 1 over 4, the integral of cos x is sine, so it's going to be sine 4x minus 6 plus c. For question C, we should recognize that we've got here a composite function where this first function here is the derivative of our second function here. So we would say that for part C we're going to use the substitution method. So we're going to say u equals e to the x. If we differentiate u with respect to x, we end up with e to the x. So you can see in this instance we're saying this is going to be our u, and then if we differentiate that we end up with this. So we can use the substitution method here. U equals e to the x, differentiate that gives us e to the x. So I can rewrite this as e to the x, we've said, is du by dx multiplied by sine of u, because we've said this is u. So we can write this, the dx and dx will cancel out, so I'll be left with the integral of sine u du, and we know from what we've just seen that the integral of sine x, or here sine u, would be negative cos u plus c, and then we're just going to substitute back in for u so that we end up with negative cos e to the x plus c. So just to remind you then, substitution method, if you have something you recognize within the function such that when you differentiate it, you end up with another function, another part of the composite function here, you can use a substitution method. So similarly in part D, we recognize that if I take the derivative of what's inside the brackets here, I'll end up with 12x cubed. So we've got an x cubed here. So in this instance, this is not exactly the derivative of this, but we can manipulate it. So we're going to start off with u equals 3x to the power 4. We're going to differentiate it and get 12x cubed. And therefore, we're going to recognize that x cubed is actually 1 over 12 times du by dx. So we can substitute in for x cubed, 1 over 12 du by dx, and multiply by cos u. And then we know that the integral of cos u is going to be sine u. So I end up with 1 over 12 sine u plus c. So all we've done here is just the dx's have cancelled out, and I've taken out 1 over 12 as a constant to enable me to integrate this simply, which gives me this here. Another couple of questions then here in terms of finding the exact value. So the fundamental theorem of calculus to, for instance, find the area under a curve. We have been given two functions here. We're asked to find the definite integral without a GDC and then to check this using the GDC. So for question 1 here, we want to find the derivative, find the integral, of 2 cos x with respect to x. So we're going to take out 2 as a constant, and left with 2 multiplied by the derivative of, the integral, the antiderivative of cos x dx, which we know is sine x. We can then substitute in for sine pi by 4 minus sine 0. Sine pi by 4 is going to be the same as sine 45 degrees, which is going to be 1 over root 2. So that's going to be, 1 over root 2, and then sine 0 is going to be 0. And if we multiply that up, we're going to get 2 times, root 2 over 2 if we've rationalized the denominator. And then if we expand that out, that's going to give us root 2, or it will give us 2 over root 2 if we hadn't rationalized the denominator. We can check that on our calculator. Just literally plug in all the numbers into the trig calculus facility on the calculator, and we should end up with an exact value of 1.41. For part B, we are going to recognize that in this instance, for part B, we are also going to use the substitution method. So we should be able to recognize that if we set u equal to cos 2x, so this would be cos 2x all cubed. But if we have u is equal to cos 2x, then the derivative du by dx is going to equal to negative 2 sine 2x. Remember that the derivative of cos x is negative sine, so we would do negative sine 2x multiplied by the derivative of what's inside the bracket using the chain rule. So that's what this would give us. And again, we can see that in here we've got sine 2x. So this is very similar to this. All I would need to do is realize that this is negative a half, multiplied by du dx. So negative a half multiplied by this would give me this, so negative a half du by dx. And then I said u was going to be cos 2x. This is cos 2x all cubed, so this is u cubed. I can then cancel out the x's, take out the negative half as a constant, and then I can substitute in. So once I've got negative half, I can find the antiderivative of u to the 3, which would be a quarter u to the 4. I've taken out negative a half here. I need to change the limits here. So whilst the limits are pi by 2 and pi by 4, when x equals pi by 4, I substitute it into u equals cos 2 times pi by 4, which equals cos pi by 2, or cos 90, which is going to equal 0. And similarly, when x equals pi by 2, I'm going to end up with cos pi equals negative 1. So I substitute in for those two values, and I end up with the value of negative 1 over 8.